Okay. Okay, it's a pleasure to introduce our first speaker of the second session, Saida Guellati. We're going to work through a Zoom talk here, so expect technical difficulties.
Okay, you hear me?
Yes. Yeah. Okay. So far, so good.
Okay. Hi, good morning from Paris. First, I want to thank Tanya, Shaiman, and Andrew for inviting me to this nice workshop. I'm really sorry. I would like to be with you in person, but unfortunately, some few contrasts prevent me from traveling at this moment. So, in my talk, I will don't have any wonderful result to show you. I just want to present you a recent work on our group in order to try to understand the discrepancy between Berkeley and Paris measurement. So, oops, what happened? Sorry. So the main motivation of our measurement of the recoil velocity or h/m measurement is the determination of the fine structure constant alpha. This currently the most accurate determination of alpha comes from two measurements, from the recoil measurement that I will discuss a long time in this my talk, and the comparison between the theoretical and experimental value of the anomalous magnetic moment of the electron. There is the prediction of the theoretical value of anomalous of magnetic moment of the electron is what we call also standard model prediction, and these count for three terms. A dominant term for the electron comes from the QD contribution, and this QD contribution scale as a series of alpha, and the idea is to provide the accurate and independent value of alpha to test the QD calculation. Currently, I show in this diagram the contribution of the first order of this QD and the hadronic, wick, and tau and Mayan and coupling contributions. And as we see, the level of uncertainty on value of alpha from h/m measurement, as well as the experimental value of G-2 are at the level of all these contributions, and progress are needed to test the weak the contribution of the weak interaction. And another side, the motivation, assuming that QD is okay and calculation are okay, the looking any discrepancy between lepton anomaly could be the way to test standard model of to look of new physics. And the major what to say puzzle is the anomalous magnetic moment of the moment. I show you in this diagram the last result, which are published in this, which now is still in archive. And we see here these are the recent experimental value and the average value. And this new result, this work, which correspond to high precision calculation of hadronic vacuum polarization contribution in the Mayan, which is the main contribution. These works seem in good agreement with the experimental result, whereas the QD approach based using experimental data show a discrepancy of about 4 sigma. And the idea also is to improve the uncertainty in the electron sector because if there are any new physics which could explain, for example, this discrepancy, it should be seen on the electron, but the effect on the electron should be small, at least its scale, assuming that the new physics scale lambda is the same for both electron and muon, the effect should be very small on the electron. And that means that if we want to see something, you have to improve both the experimental value of G-2 and also the predicted value by the standard model. So our approach, we determine alpha from the measurement of the ratio H/m using this simple formula, where you have here Rydberg constant, relative atomic mass, and relative electron mass, and H/m ratio. And in this, the uncertainty on alpha is limited by currently by this term. And there are two groups in the world working on this experiment, a group of Olga Müller at Berkeley, who work on cesium, and our group in Paris, we use rubidium. So I show you this, the contribution to delta E of different uncertainties. And if, for example, we need to see on the electron 4 sigma discrepancy, I put this, we should achieve at least this level of uncertainty. And we see that we have, and if we want to see effect at 3 sigma, to be sure, and we should to achieve this uncertainty. That means that many people have to work together, recoil measurement, G-2 experiment, as well as mass measurement of cesium and rubidium. So I just, let me say some word of the principle of experiment in Paris. Sorry, some people saw this slide many times. So in the group, we measure this recoil velocity of atom that absorb a photon. This velocity is about 6 millimeters per second for rubidium. And the principle of the experiment is too simple. We transfer to the atom using Bloch oscillation technique and optical lattice about 1000 recoil velocity. And we measure the Doppler shift induced by this change of velocity by using atom interferometry. And then the uncertainty on the recoil velocity measurement is given by the sensitivity or the uncertainty of our atom interferometer divided by the number of recoil transferred to the atoms. We have to measure this velocity. We have a velocity sensor based on atom interferometer. And then we use the Ramsey-Bordet atom interferometer, and which consists on 4 p/2 pulse. Each pulse induces a Raman transition between the 2 hyperfine level of fundamental state. And the first p/2 act as beam splitter and create a coherent superposition between the two states, these two states. Then the second one put the atoms in the same internal state. In the middle, we switch on our optical lattice to perform Bloch oscillation to transfer to the atom a large number of photon momenta, which induces delta P variation. And then we close our interferometer by 2 pair of p/2 pulse. And finally, the probability to find atom in state 1 or 2, for example, 2, depend on the phase shift between the two arms of the interferometer. And we can calculate this phase shift using Feynman path integral, and it depends on the mean velocity between of the atom times the separation between the two arms. More precisely, this phase shift is given by h bar over m times to the number of recoil, the wave vector of the Raman beam and Bloch beam times this Ramsey times. And we to scan this phase shift, we to probe this phase shift, we have to scan the phase of the laser. In fact, we scan the phase of the laser to compensate the Doppler effect induced by this change in velocity. The experiment is simple. We produce a cold atomic source here, and then we this is the trajectory of our atoms. We apply Bloch oscillation sequence to perform what we call atom elevator, and atoms come there. And in this area, which is interference area, we control perfectly the magnetic field. And then the atoms, during the free fall of the atoms, we apply our interferometer sequence or our measurement sequence, which consists in two pairs of Raman beams in yellow, and the red one is Bloch acceleration that transfer 1000 recoil to the atoms. And finally, we measure the number of atoms here in this area in state 1 and in state 2 by using time of flight technique. Here I show you typical atomic fringes, and we are able to determine the central fringes with a certainty of about 50 millihertz. And these which correspond to sensitivity to the recoil velocity of about 20 nanometer per second, this, which correspond to uncertainty on h over m to 310 to the -9 on 1 minute integration time. In fact, the protocol of measurement protocol is quite different. In fact, if you look accurately the phase difference between the two arms, we have to consider the gravity and also any level shift. And to cancel both gravity and level shift, we use we first accelerate in up and down direction to cancel g, and we change the direction of this k vector to cancel constant level shift. And by combining these different center measurement, we extract a value of alpha. So this our statistical uncertainty on the measurement of 2020, and we achieve a relative statistical uncertainty of 4.310 to the -11 on 40 about 50 hour integration time. And recently we improved this statistic by factor 2. So all these results led us to a determination of alpha at 10 to uncertainty of 810 to the -11, and we comparing to our previous value in 2008, we identified a new systematic effect. And this value also, in fact, in the new assay, measuring h over m is also a way to what we say mise en pratique of the kilogram at the atomic scale. And our experiment measured the atomic mass, and this is the most accurate measurement of atomic mass. Also, as we know, in the new assay, some the fine structure constant play also an important role in the adjustment of the fundamental constant. And as you know, the new aside, the numerical value of epsilon 0 and mu 0 will depend on alpha, and these measurements give also now the most accurate. And these results allow to improve the uncertainty on about 90 fundamental constant listed among the one listed by NIST. So, but there are big problem. The big problem that, as you see, I here in this diagram, I show all the determination of the fine structure constants, both from H over M and G minus 2 measurement. You see that, and here this is a zoom. This is the new value from Gabriel's group. And we see that there are big discrepancy between Paris and Berkeley measurement. And this discrepancy should be resolved as soon as possible. And so this, in the last 2 years, we spent a lot of time to try to improve and to understand the origin of this discrepancy. And for that, we need to come back to our budget error. If you see here, the main systematic effect come from the wavefront, because the problem. Sorry, oops. Okay. In fact, we measure the atomic phase to extract, and then we extract the ratio H over M. And we need to know precisely the K vector. Unfortunately, we don't have plane wave. At the best, we have a Gaussian wave, and then we have to make to calculate the correction due to the profile of the laser beam. This correction is due to the curvature of the wavefront, to the Gui phase terms in the case of Gaussian beam, but also is due to the local fluctuation of the intensity. In this paper, we demonstrate a major result for atom interferometry, and we show that for this the correction include a phase term, but also a term that depend on the Laplacian of the intensity. And also, as the Bloch oscillation efficiency depend also on a laser intensity, there are a correlation between the correction and the efficiency of Bloch oscillation. And as you see here, in the area where the Laplacian is hard, the efficiency could be smaller if we are just at the threshold of the close to efficiency equal 1, and then we can lose some atoms here, and other atom in these at the maximum survive, and in the averaging this distortion affect the correction of the key vector. And all the problem for such measurement is how to characterize perfectly the profile of the laser beam. This is the main challenge. Even we measure with Shah-Hartman or improved optical technique, the problem is what the profile seen by the atom inside the vacuum chamber. This is the big challenge. And recently, what we do, we try to do measurement with Bose-Einstein condensate, and then what we did, we do a measurement by alternating Bose-Einstein condensate and optical molasses. And that what we see that for optical molasses, the mean value is still constant. For here, we do measurement over all the week, but for the condensate, we see some fluctuation. And we see here on, voilà. And we show that we observe for the first time a temporal fluctuation of the H/M by using Bose-Einstein condensate. We never saw observed this fluctuation with optical molasses. And we try to understand what happened. And for that, what we do, we do measurement only with Bose-Einstein condensate by varying the position at different position of on the transverse position of the laser beam. And what we do, how we do that, we only impart a transverse velocity to the atom at the end of the evaporation process. We just change the frequency of the AOM, acousto-optic. And we was able to reproduce the fluctuations that we saw over 3 days. In the same time, we did numerical simulation for a small temperature and large temperature for molasses and Bose-Einstein condensate, and we saw the same effect. And this effect, of course, average for the optical molasses. And the good news, in fact, the size of the condensate is too small, and the condensate is able to probe in situ the profile of the laser. Finally, this result is very good news, because that means that we have a method that we are able to probe the profile inside in situ. And for that, what we do, we develop a new collimator. This is the profile of the laser beam with the old one. And this is the usual technique by propagating the beam at short size. And after collimation, we are able to smooth the profile of the laser beam. And in the same time, what we do, we use a larger beam splitter in order to avoid some diffraction. And what we see recently, we see this one measuring with back over 60 hours. We see that there's a fluctuation. And when we look more closely, we see that this fluctuation corresponds to fringes. And in fact, we observe that the new PBS cube induce parasitic reflection that induce interference, and our method allow to see this interference. Recently, we have used a polarizing plate beam splitter, which give more flat profile, and we hope some promising result. The conclusion of this work that we should do measurement with not Bose-Einstein condensate is not good for measuring H/M, but is good to evaluate systematic effect due to the distortion. However, to do measurement, we should use optical molasses, or at least by using the technique of lensing technique, which in fact we need large atomic cloud to average the local fluctuation. In the same time, we do also some just few words about this second effect, due to the phase shift in Raman phase lock loop. In fact, as we, in fact, between the two pair of Raman beam, we have to sweep the frequency of the laser to compensate the gravity and to still in resonance with the laser. And these induce an electronic phase shift that we discover by studying systematic effect in 2022. In this previous measurement, we only phase lock the laser after the doubling process. In fact, this is the 2-Raman laser. And how we produce our laser source, we double 1.5 micrometer. We amplify this laser and then we double it to obtain a 780 nanometer. And on our previous measurement, what we do phase lock after this doubling. And recently, we have 2 stages of phase lock, one before the doubling and second after one, and we see that these improve the sensitivity of our interferometer. And more recently, we also developed a new setup for measuring this electronic phase shift. How we measure? In fact, we extract a part of the signal from the bit node signal, and then we do this technical problem. I don't want to spend time on this, and then we measure the phase at different this phase for different laser pulse of atom interferometer, and then we use this value as correction of H/M measurement. And currently, we are doing 3 independent blind measurement by 3 independent person with 3 independent analysis method. And we hope that we will confirm definitively this effect. To conclude, all the time that spent this last year is to try to improve our experimental setup. We demonstrate a new robust method to probe in situ the laser beam profile using Beck, and we develop a new simulation code to analyze this data. Currently, I hope that new measurement campaign is coming soon. Everything is working now. We also want to measure by using Berkeley group protocol. The idea is to use Bragg diffraction and Bloch oscillation. We use exactly the same protocol to check if the discrepancy comes from this. And in the same time, we started 3 years ago a new experimental setup for measuring H/M with ytterbium. Okay, thank you for your attention.
Okay, questions? Shimon.
So it looked like that if you and Holger are able to improve your measurements a little bit, you'll soon be limited by the mass measurements of rubidium and cesium, if I understood your plot correctly, when you were showing the work that needs to be done. Are there prospects for improving those independent mass measurements?
Yes, I think there are progress of mass measurement. We are currently trying to make a strong collaboration with a close group at Heidelberg and also with people from UK and Hanover to try to measure with ytterbium, strontium on short scale and large scale interferometer. And we include in this consortium the group of Heidelberg, and they say there is not problem.
Questions? Well, as the chair, I'm curious to hear more about the prospects of using ytterbium, pluses and minuses for improving precision.
Sorry?
I can hear you, but not me.
I think it's an owl.
Turn it around.
Oh, I got
Better.
I'm
Hello.
sorry.
Can you hear me now?
Yes, yes.
Okay, great. I was just curious to hear more about the prospects for using ytterbium to improve on the measurements of alpha and pluses and minuses and what goes into that.
No, improving using ytterbium is not improving. If we have many spaces, we have many values. This is the way to improve the confidence of on alpha. But the goal is also to use different approach of atom interferometry. With ytterbium, we will use Bragg diffraction to implement atomic beam splitter, and we hope to use the clock transition for that. And the idea is to cross method of concept of atom interferometry also of spaces. And we have other reason to use ytterbium, but it's for another experiment.
Thank you.
Mm-hmm.